Let's start by reviewing how the blast furnace works. It processes a mix of pellet, sinter, lampor, and coke, sometimes with the injectant like pulverized coal. The main driver is gas flow, enabling reduction, heat transfer, and vital chemical reaction. Remember, temperature in local zones influences reaction progress, which means our body input determine output quality and furnace stability. Now, as for the hot metal and slag quality is concerned, it is one of the very important objective of blast furnace. So next, what to do we want from our output? Let us see. Hot metal should have around 94.5% iron, 4.5% carbon, 0.4 to 0.6% silicon, and tightly controlled sulfur and phosphorus level. Slag must be low volume and composed mainly of alumina, magnesia, silica, and lime. Constraint include giving phosphorus and alkali, how to avoid damage and minimizing zinc to prevent cycles. Raw material choice directly affect these results. Highly alkali burden means absolutely full of disturbance. As far this table summary is concerned, here summary of hot metal and slag targets is shown. Here is our composition targets. Hot metal should be of iron 94.5%, carbon 4.5, silicon 0.4 to 0.6%, for slag alumina 8 to 20%, magnesia 6 to 12, and all those. Refer to this table when adjusting burden and monitoring the output. Now let's move on to burden calculation. Single stage mass balance on a dry basis helps hit our desired viscosity such as CO by SiO2 at round 1. For example, a burden mix of 70% sinter, 20% pellet and 10% lampor gives slag at 250 with silica 34, alumina 13, CaO 40 and MgO as shown. Every input like sinter at almost 1100 kg per ton directly impacts slag composition and process basicity. One stage mass balance is very important aspects in blast furnace. Now let's discuss these mass balance with respect to or Bosch gas coming from the TUIR includes which includes nitrogen, carbon monoxide and hydrogen. After reduction, the top gas contains carbon monoxide and S2O from a reaction byproducts. A typical input 900 meter cube wind and 200 kg coal per ton create a top gas of 46% nitrogen, 5% hydrogen, 26% CO and 22% CO2. Oxygen balance and hydrogen utilization link or inject into overall efficiency. Now here is a quick look at top gas numbers for each key component. For 1 ton of hot metal, nitrogen, hydrogen, carbon monoxide and carbon dioxide is shown. This table helps visualize the outcome of inputs uh, adjustment. Now let's examine the temperature profile. The burden enters the FeO, Fe to O3 and is reduced to FeO at 600 to 900, then further iron above 900. At 1100 both direct and indirect reduction occur, and key reaction as it is already mentioned in the slide also, The FeO react with CO and carbon to form iron and CO. The thermal resolve zone stays near 1000 degrees centigrade, occupying half the furnace height. Direct reduction remove 30 to 40% oxygen and consume about 100 kg of coke per ton of hot metal. Now moving to carbon balance for each 1 ton, uh, 500 kg coke is charged, about 45 kg enter hot metal, 100 kg goes to direct reduction and rest exit as top gas. Data shows direct reduction uses around 91 kg of coke for iron oxide. Any increase here speed the Bodin descent but may promote cooling. Track via gas composition and secondary fuel injection. Now let's tie everything together with the operational takeaways. Bodin choice affects slag and gas output, balances mass flow and impact temperature and reaction efficiency. Direct reduction variability can cause cooling and operational instability. So real time does and gas monitoring is crucial. Optimizing burden for target oxygen removal lowers coke use and boosts productivity. Effective heat transfer matter most for the control slide.